My name is Tasos Moulinos, and I'm a postdoc at the University of Toulouse, currently working with Bertrand Tohen. My research broadly lies in the areas of algebraic topology and algebraic geometry. Using the framework of higher algebra and derived algebraic geometry, I study cohomological structures arising from topology, geometry, and arithmetic. Higher algebra, or algebra formulated in the setting of higher category theory, replaces the basic algebraic objects, like a ring, a vector space, with their higher dimensional analogs, simplicial commutative rings, for example, or ring spectra, and their modules. Derived algebraic geometry, which is algebraic geometry based on higher algebra, allows for one to glue these together to obtain what's called derived stacks. Many mathematical phenomena actually have an underlying homotopically coherent structure and may be encoded cohomologically in this world of derived stacks. Okay, so a key theme to have manifested itself in my work is the geometric interpretation of a notion of filtration. Filtrations are both of computational and theoretical value. They allow for computations via spectral sequences by decomposing an invariant into more computationally accessible pieces. There's a geometric approach to filtrations that goes back to the work of Carlos Simpson on non-abelian Hodge theory. So I include a little bit background on filtrations here. So the idea of Carlos Simpson is that filtrations on a vector space or a K module are the same thing as vector bundles on the stack A1 mod GM, where this is the quotient stack of A1 by GM, which acts via the standard inclusion on A1. And this stack comes equipped with two distinguished points from spec K, which we call the generic point, and the close point from BGM. Notice that this is itself a stack, BGM. Pullback along either of these maps recovers the associated graded construction. So you get a graded object when going to BGM, or the underlying object of the filtration when you pull back to spec K. So the first result I want to go over here is a result of mine in the setting of spectral algebraic geometry, where this takes on a particularly nice form. So there's a spectral analog of A1 and GM. This is the flat affine line. And my theorem is that there's a symmetric monoidal equivalence of stable infinity categories, where on the left we have the category of quasi-coherent sheaves on the stack A1 mod GM. And on the other, and this is the derived level, infinity categories. And on the other side, we have filtered spectra, filtered objects in spectra. Now, under the above equivalence, the associated graded functor is naturally identified with pullback of quasi-coherent sheaves along the map BGM to A1 mod GM, and underlying object functor is just pullback from QCO A1 mod GM to spectra. This equivalence specializes to all previously known or expected identifications, such as the one motivating Simpson's work. Moreover, it allows us to display filtrations on like a ring spectrum, for example, or the cohomology of a stack, in most general situation, by exhibiting a map from X to A1 mod GM. And our first application of this framework is to Hochschild homology. Recall the Hochschild constant Rosenberg theorem, which identifies the Hochschild homology of a ring with n forms. In characteristic 0, this is actually there's more structure. There's on the one hand, we have the derived complex, where we can view the S1 action as being the derived differential. And this is a graded complex, and so the derived differential raises the grading by 1. And on the other, we have Hochschild homology. And this is an S1 equivariant equivalence of algebra objects in the derived category. In characteristic P, however, this identification drastically fails. So the idea the work that I'm about to describe is my collaborators and I construct a filtration on Hochschild homology, exhibiting the derived algebra as a degeneration of Hochschild homology. And this should also be compatible with the S1 action, which Hochschild homology has, so that one gets a filtration on other Hochschild invariants, like negative cyclic homology. So, motivated by the notion of affine stacks and the schematization problem of Grothendieck, we construct a higher stack which admits a map to A1 mod GM. And the cohomology of this stack agrees with the cosimplicial algebra of cochains on the circle, on the topological circle. Rather surprisingly, this stack arises as the classifying stack, BH, of a filtered group scheme, which itself interpolates between the fixed points and the kernel of the Frobenius operator on the bit vector scheme, W. And this is our theorem. Well, this is with Roballo and Toen. So we construct this filtered stack. It emits a map to A1 mod GM, and we describe its pullback to spec K. The cohomology of that is precisely cochains on the circle, both as an E-infinity algebra and as a co-simplicial commutative algebra. Similarly, the pullback to BGM, we call this B-cur, and this is the trivial square zero extension of K by K minus 1 placed in weight minus 1. This is again as co-simplicial commutative algebras. And that's an important structure to keep in that we identify. So in order to, what we've done is we constructed an algebra geometric avatar of the topological circle, which naturally has a filtration. By taking the derived mapping space of maps out of it into an arbitrary derived scheme, which we call the filtered loop space, we recover Hochschild homology as the global sections of the pullback. So before I say that, like the global sections of this filtered loop space has a structure of an S1 fill representation. This is S1 fill is actually an abelian group stack. Base changing to spec K recovers Hochschild homology, recovers the ordinary loop space. Base changing to BGM recovers the shifted tangent bundle, in other words, the derived DRAM algebra. And applying S1 fill fixed points, we get a filtration on negative cyclic homology. In the process of writing this up, we discovered this was an instance of a more general construction. To G a formal group, one could take its Cartier dual, which is an affine group scheme. This affine group scheme, we can take the classifying stack, and then we can take the derived mapping stack of maps out of this into an arbitrary derived scheme. We call this G-twisted Hochschild homology. And when G is GM, the formal multiplicative group, one recovers Hochschild homology. And this brings me to an objective, which is to study this assignment in the following two cases at least. When G is the formal completion of an elliptic curve, or when G is a height n formal group, in particular for the Lubin-Tate formal group. As part of ongoing work with Marco Roballo, I'm interpreting the Witten genus in the elliptic curve setting. We think we potentially have a global construction of the Witten genus using derived algebraic geometry over the moduli stack of elliptic curves, potentially. In other work, I'm looking at, again, the Lubin-Tate formal group over, and this is actually the Lubin-Tate formal OK module, over the ring of integers in the local non-Archimedean field. And in this case, I obtain an isomorphism of group schemes relating the Cartier dual of this formal group with the spectrum of the ring of integer valued polynomials of OK. And this is actually a group scheme. And this is actually analogous to what happens integrally or over RP locally. And some miscellaneous projects. I've had a long-standing interest in K-theory both on the computational and theoretical side. In recent work with Oscar Bayandir, I compute the K-theory groups of THH of FP using a functorial decomposition on the cyclic bar construction of a particular graded monoid in spaces. In my thesis, more on the theoretical side, I constructed a relative version of topological K-theory as an invariant of DG categories. This is over the complex numbers. This is of a non-commutative motivic flavor and has since been used by other people to tackle a categorical version of the integral Hodge conjecture. Last but not least, I am currently thinking a lot about prismatic cohomology. Drinfeld recently constructed a stacky formulation of the theory, which uses actually many of the constructions that arise in our HKR paper. So I'm currently investigating whether or not there exists a prismatic analog of the filtered circle, or at least some of the constructions that we use. So this is obviously work in progress. So here's some references. Thanks for watching, and thanks to the organizers for this cool event.